Okay. So, um, as mentioned last time, um, there are five kinds of aberrations which come about because of the use of lenses. Okay. So we took a look at spherical coma, astigmatism, and curvature of field. Right. So spherical aberration appears when the rays which are farther away from the center of the lens focus closer to the lens. Okay, so that is spherical aberration. Then we talked about coma, where the rays that are not parallel to the optical axis, okay, focus at different points. Okay, so the oblique rays don't focus at the same place where the parallel rays focus. This causes coma. Then astigmatism, we saw, is where the light comes to focus either in the either in front or behind where it is supposed to focus. Okay. So that's astigmatism. Curvature of field is when the various rays focus on instead of a straight plane, that's the sensor. They focus on different points which sort of form a curve. Okay, so that's called curvature of field. And now the important point is that all these four kind of aberrations that we saw earlier, they have to be fixed at the level of image taking. Okay, they are not something that you can fix in pre-processing. So this is why you need to be aware of these things. Okay, so if somebody comes to you with a set of images and says, okay, do this for me, and you see one of these aberrations, then you have to go back to the image taking process. Okay, you cannot hope to fix these kind of aberrations in any kind of pre-processing. Okay, if they are causing a problem to your processing. Okay, if they are not causing a problem, you don't have to worry. But far as I know, well, these spherical and coma, these will definitely, that's a blur, right? So it will definitely cause a problem. Curvature of field will cause problem for measurements. Okay, so these kind of things you have to be aware of. The last kind of aberration, which is distortion. Okay, this is something that can be fixed in pre-processing. Okay, so distortion is of two types. There is tangential distortion and radial distortion. Okay, and radial distortion again looks like two types. There is what's called as the barrel distortion or the pin cushion distortion. Barrel also sometimes it's called fish eye distortion. Okay. So let's take a look at what each of these means. Okay. So radial distortion means the distortion is along the rays about some center. Okay. So in a circular fashion, this is radial distortion. It's along the radius of a circle. Okay. So if you look at this figure a bit closely, I don't know if I can zoom in. Yeah. No more. Okay. So if you look at this figure closely, the blue points here, okay, are where the image points should have been focused. Okay. And the red points are where they are actually focused. Okay. So the displacement is radial in the sense that this point is focused a little ahead along the direction of this ray, okay, which is the radius of some circle. And along the same radius, along the same distance, but along the different rays coming from the origin, you see these focusing. Okay, so you see these displacement. The blue is the ideal position, the red is the actual position. Okay, so the actual positions are along this circle, and the displacements are along uh, along these rays, which are along the radii of the circle. Okay, so this is called a radial distortion. Now, this distortion can be so that the red point is ahead of the blue point, if you look at it from the center, okay, or it could be before. Okay, so your actual position is this, and sorry, your ideal position is this blue point, and your red point could be focused somewhere in before. Okay, so your red points could be lying on a circle of smaller radius. Okay, so there are these two possibilities, right? Either it is beyond these blue points, or it is before these blue points. So if it is beyond, it is called as barrel distortion. If it is before, it is called as pincushion distortion. Okay, because if these points are pulled closer radially, okay, then it appears like your like a pincushion. You know what a pincushion is? So a pincushion is where you know, or you can just imagine that you have a cushion, square cushion, and you have put a pin in between, so that it is compressed in between. Okay, and so the shape of what will happen to the sides of the cushion, it will curve like this, right? If you put a pin in between, the cushion will curve like this. So that's why it's called a pin cushion. Pin cushions are actually these little cushions designed to hold needles. Okay, that's what a pin cushion is. Anyway, so because the distortion appears in an image like this, it's called a pin cushion distortion. On the other hand, barrel distortion, do I have the image? Yeah, here. Okay, this is a barrel shaped distortion because radially the points are being projected, and this is happening to every point, right? So the effect is like this. Okay, so if you see this kind of effect in your image, that's a barrel distortion. On the other hand, if you see this kind of image effect, it's a pincushion distortion. Okay, this is how the actual image should look like. So in this image below here, you can you tell me what kind of distortion do you see in this image here?
Pincushion, I
Pincushion.
guess.
It's pincushion, right? So you observe, look at this. This is the horizontal line, the edge of the image. And look at this thing. Look at these edges. These are supposed to be parallel to the edge of the image. But because, you know, they are parts of a building and you expect them to be straight. Okay. And they are relatively straight here. But these are not. Okay. So this is pincushion distortion. And you can see the other type also. I'll have some more example images. But let's come back to this. Okay, so that is what. So that is what a pincushion, or sorry, radial distortion means. Okay. On the other hand, a tangential distortion. So see, radial distortion occurs along the radius or along this ray from origin to the expected ideal position. So that is radial distortion. Tangential distortion occurs in the direction tangential to this ray. Okay, tangential means so this if your ideal position is here and this is the radial direction of radial distortion, your tangential distortion will be perpendicular to that. Okay, so at this point in this direction or in the other direction. Okay, so that kind of so the effect is like this. Okay, so your ideal position now again these blue points are the ideal position and red points are the actual positions. Okay, so the effect for the image is what you see here. Okay, so this grid is sort of tilted to one side. Okay, and if you could, this could go the other way also. Okay, in which I mean, other way means here the red points would have been on the left side also, west side also. And then in that case, you would have the image tilted a little bit to the left side. Okay. So what this is what is called as tangential distortion. Okay. Now the reasons why tangential distortion or radial distortion occur can be those reasons I will discuss, and these can be corrected using what is called as the camera matrix, which we will compute. Okay. So the camera matrix is useful in undoing these kind of distortions, the tangential and the radial distortion. So this is something that can be corrected in pre-processing. So for example, this image can be straightened out using pre-processing. Okay. You remove this radial distortion. This is barrel shaped distortion. Okay. So really bad distortion. You can see the pillars absolutely curved like this. Okay. Whereas these, the ones that are so as you can imagine, the effect of barrel distortion is worse towards the edges. Oops. Okay, like you can see in this chessboard image. Okay, towards the center you might not even notice. Okay, it can be very little, very uh, unnoticeable, but towards the edges, that's where you should look. Okay, it's the same goes for pincushion. Towards the center, even in this earlier image, towards the center, I mean, if you had only this much, you would not have noticed it. But if the field of view is increased, then that's when you notice it. Okay,
Ma'am,
just like this. Yes,
so over here, in both the cases, the radial distortions are about the center of the image. That's why it's appearing that the center is not affected.
yes, yes.
But it could be in one of the corners of the images
Yes,
too, such that
yes.
the corner is just like that. And
Then you would have to suppose the image center was here. But see, uh, yeah, this also you have to remember that you have to talk about optical center and image center, right? You are probably talking about the optical center right now, correct? You want to say that the optical axis is focused here, for
yes,
example.
yes, yes,
Then you would be looking at the more distortion on this side, the
yes,
opposite side.
as well as the center would be center of the image would also
Yeah,
be.
here also you would see more effect than you see here, for example.
Yes.
Yeah, that is true. Okay, so all these things have to take we can take into consideration. Okay, the optical center and the image center, are they aligned? And what is this distortion can be modeled mathematically, and it can be therefore corrected. Okay, so all these things can be done. Yeah. So as I was saying here, radial and tangential distortions are entirely lens errors. Okay, they arise from the fact that straight lines are not mapped to straight lines by the lenses. Okay, the lens is doing this, creating this effect. Then they can be minimized. First of all, you can minimize it on the image taking level itself. Okay, so trying to focus in either you reduce your field of view, okay, or you use the correct kind of lens. Like don't use a close-up lens for a wide-angle picture, or vice versa. Okay, so using the correct type of lens for the distance that you want to cover and the field of view that you want to cover. Okay, so that minimizes this distortion. Okay, and also focusing properly. These kind of things minimize distortion on the image taking level. But you can also undistort these things or remove this effect on the pre-processing level. Okay. Uh, Yeah, so the last point here I want to make is you have to differentiate between radial and tangential distortion and perspective distortion. Perspective distortion is when parallel lines are not mapped to parallel lines. Okay, see perspective distortion, there is no correcting about it. Okay, perspective distortion appears simply because what we saw earlier, what we saw in that lecture about how an image is formed, right? It is simply an artifact of the imaging process. It has got nothing to do with lenses. Perspective distortion will occur even if you have a simple pinhole camera, no lens. Okay, so you should, in your mind, it should be clear what is perspective distortion. The railway tracks not appearing parallel throughout the image, that's not radial or tangential distortion. That is simply perspective distortion. You cannot expect parallel lines to be mapped to parallel lines. So that is perspective distortion. And you should be able to recognize what is radial and tangential distortion so that you have hope of correcting it. Okay. Okay, so so I have used like various, so these are just references. You can look at these references if you're more interested. By the way, there is a set of lecture series by Cyril Stackles on photogrammetry. Okay, so at least the early lectures in his photogrammetry course. So that course is designed for an entirely different purpose. It's called photogrammetry. So you don't need to look at too many of those. But some early lectures focus also on this part of camera basics. Okay, so also he also explains in a very nice way. So if you have time, you should take a look at Cyril Stackman's photogrammetry lectures on YouTube. Okay. All right. So let me stop sharing this. And are there any questions about all that? Uh, because if there are not, I will move on with the next topic. No questions? Okay. So just give me a moment. so that we can get started with. I want to talk today, that is a bit of projective geometry. Yeah. Yeah. Here. This will be our fifth lecture, right? Okay, this is what I want to talk about. Yeah. No, this is not the one I want to share though, because I want to write. Yeah, this one. Okay, so we will talk a little bit about projective geometry. Are you seeing the screen? No, I didn't share. Sorry. So we will talk a little bit about projective geometry because this is the model, or this is used for modeling the imaging process, okay, the mathematical modeling of the imaging process. Now I'm going to assume that nobody in this class has ever heard of projective geometry. That is going to be my assumption. And so if you already have heard about it and you are comfortable with it, then you need to bear with me. And on the other hand, if you have never heard about it, then I would strongly suggest you not to worry too much about it, because the repercussions of this uh, are in, I mean, even if you don't entirely understand this whole process, you will still be able to calculate the camera mode. Okay. But you need to have some understanding of this process in order to understand how that whole camera matrix appears. Okay. So that is why I'm doing this exercise of going over this modeling process. Okay. All right. So what we saw in the third lecture, or the one before it, when I described the pinhole camera model to you, we looked at the geometry, right? We were entirely looking at the geometric picture, and we had not assigned coordinates or anything, right? Now, in general, use of algebraic language over geometric language is preferred, especially if you are into computing, right? Because it is this algebraic language that will help you derive algorithms and procedures for computing the required quantities. So that is why we want to look at algebraic methods. And for camera matrix, for computing this or understanding the imaging process in a camera, it turns out that the language to use is that of projective geometry. Okay, so let us see what is projective geometry, why we need it. Okay, then I will talk a little bit about the elements of 2D projective geometry, two-dimensional projective geometry. Okay, and in that I will briefly describe how the points look like, how the projective plane looks like, how lines and conics look like, and what is the projective transformation. And what we want to do with all this is we want to describe the pinhole perspective as a central projection, okay, a type of projective transformation. So now we will take our geometric pinhole perspective picture and get it, try to write it down in terms of a projective transformation with coordinates and everything. Okay, so that is, and then in the fourth part, we will see how we can remove perspective distortion. Once we have everything in this coordinate form, how perspective distortion can be dealt with. Okay, so this is the agenda for today. Okay, let's see. Maybe I will be able to cover only till 3, but we'll see. Okay, so what is projective geometry and why we need it? So if you have seen images, okay, generally you will see that the pictures that you take, shapes do not appear like they actually are. Okay, so for example, if you've taken the picture of a, so I'm saying from various angles, okay, from a particular angle, you may be able to preserve a particular shape. Okay? But so if you take, if you're looked at images of circles, they will not appear as circles exactly. Okay, so suppose you are taking pictures of dining table with food on it. You know the plates are circular, but they don't appear circular in your image, right? So circles are not mapped to circles. Ellipses not mapped to ellipses. Squares not mapped to squares. Those kind of things, right? And so all these, we know that these shapes are not preserved in the image taking process. Okay? Angles are not preserved. Distance is not preserved. Ratios of distances are also not preserved. Okay? So all these things get lost when the image is taken. Okay? And you need to recover all these. But what is preserved, and this is what this sort of determines the choice of projective geometry. What is preserved is straight lines. Okay, so straight lines go to straight lines, and that is very important for us. Okay, so in the image taking process, if nothing else is preserved, straight lines are still going to straight lines. That is what we saw in the pinhole perspective. Right? What does not happen is parallel lines don't go to parallel lines, right? But straight lines are going to straight lines. So now what we want to do is we want to talk about, so since parallel lines are not preserved, okay, we don't want to keep on, when we talk about points in the plane, we don't want to keep on singling out parallel lines. Okay, so like in 3D coordinate geometry that you studied so far, or Euclidean geometry, okay, in the postulates, always there will be that parallel. So you will have a postulate, then there will be a special postulate for parallelism, right? What projective geometry does is it sort of tries to get rid of this extra postulate. So you don't have to keep on making a special case of parallel lines. That's what projective geometry does. Okay. And so for us, the effect is going to be that we will be focusing only on the fact that straight line goes to straight line and trying to normalize or try to look modulo this parallel lines not being preserved. Okay, so that thing we are going to try and ignore when we go to projective geometry. These are sort of the abstract implications. Okay, I will talk about what are the more practical implications for us. Okay, so what is the projective space? Projective space is nothing but your, for example, R2. Okay, so if you have, let me start writing here. Oh, what happened? I will have to close this and open this again. Sorry. Um, I have to open this note again. Yeah. Okay. Yeah, there it is. So what is the projective space? So you do the following thing. You have your R2, right? R2 means the set of all points, okay, on the plane, together with the assumption. So along with the usual postulate that any 2 points form a line, and you have the additional postulate that parallel lines do not meet. Okay, so instead, or another way of saying that is saying that parallel lines meet at infinity. Okay, so what you do is you take R2 plus you take the postulate that parallel lines meet at infinity. Infinity, correct? So which means you take R2 union, uh, I'm not saying that infinity is a point. I'm saying the notion of infinity. Okay, so you take R2, which means the set of all points x comma y such that x and y are in R. Union, you take the notion of infinity And these two together will define what is your Euclidean plane. Okay, the infinite plane. Okay, so now instead of, so you have all points here, x comma y, and you have the special point here. Okay, so instead of having these two kinds of points, okay, what projective geometry seeks to do is call these points as infinity also part of the set. Okay, so from R2 to union infinity, you try to define the projective space P2, where what is projective space? Projective space is nothing but this as a set. It is just R2 union all the infinite points at infinity. Okay, so let me just say points at infinity. Okay, actually that is what I should write here so that there are no problems later on. Points at infinity. So if you look at it as sets, I'm not changing the set of points. So I'm not changing the object. What we are changing is the way of viewing them. Okay, we are changing the axioms, and we will also change the representation. Okay, so it is the same set. So at set level. Okay, now how do you write points in the Euclidean plane? In the Euclidean plane, you write points as pairs x comma y. Let me write as a vector only. X, y, where x and y are both in R. Correct? This is how you express a point in the Euclidean plane. What we will do is here. So I will come to the reason or the motivation behind writing it like this. We will write the points as not x, y, but as x, y, t. Okay, where or x, y, 1, if you like. Okay, where x and y are in R. Okay, so instead of having two coordinates, we will have these three coordinates where this is sort of a dummy coordinate, and there is a way of going back and forth between these two. Okay, if you just have the coordinate of a point, so the point x comma y is actually the point x comma y comma 1 now. Okay, but it is not just this one point. We will see it is actually a class of points. Every point here is a class of points here. We will do that. And what this is going to do is this is going to take these points of infinity and express them with coordinates. That is the main uh, or the sort of output for us, that these points will no longer be treated separately as they are done in Euclidean geometry. These points will now be treated as normal points. Okay, and you can deal with them normally using matrices as you would deal with them here. Okay, so that is what is the upshot of the whole thing for us. Okay, so now let's take a closer look at why we need to do all this. Okay, so why do we need projective geometry? One is expanding the plane and the notation to include points at infinity. That's what I was just describing here. Okay. And then when you want to talk about change of coordinates between two coordinate systems. Okay, so here is an example of why we need this expanding the notation. Why we need to expand this notation. So let's look at this example. So you're looking at change of coordinates between two coordinate systems. Okay, so the way this can be described is you have a rotation and a translation. Correct. In general, if you want to do change of coordinates, okay, you are working say with this coordinate system, and suppose your new coordinate system is this. Okay, so your origin was here, and now you want to put the origin here. Your x and y axis were here, and now you want to call these x prime and y prime as your new coordinate axis. So you want to do this change of coordinates. Okay, how will you achieve this change of coordinates? You will have to do a rotation and then a translation. Okay, or you do a translation, then a rotation. But the point is, it's going to be a composition of a rotation and a translation. Okay, so the simple action of changing coordinates, change of coordinates, involves these two things, rotation and translation. Okay, now if you use your 3D coordinate geometry, okay, your point xy under the rotation will go to some r times xy. Okay, so if r is your rotation, it will go like this. And then for translation, what you will have to do is you will have to do plus some x tilde y tilde, right? So in this coordinate system, if the address of this point is x tilde y tilde, okay, then you will have to do this to put the origin there, correct? Now what happens is this operation of translation is not a linear transformation, correct? You've seen this in linear. Translation is not a linear map. You can check if you like. That means if you want to send x comma y or xy to x plus x tilde, y plus y tilde for a fixed x tilde and y tilde, you can check that this map is not a linear transformation. Okay, translation is not a linear map. So what happens is that this entire operation of change of coordinates can no longer be expressed as xy going to some matrix times xy. Okay, so this is the practical fallout of not having translation as a linear map. So you will not be able to express this change of coordinates as xy going to some matrix times xy. Okay, but this is what we want because we want to be able to describe the entire imaging process as the world point, and a matrix applied to it being your image point. Okay, so you applied some matrix to the world point and you got your image point. That is where we want to go. That is what we want in the end. Okay, but because of this, you will not be able to express it this way. So it turns out that the Euclidean geometry or Euclidean, coordinate axis like this is not the best way of looking at points. Okay, so this is why you want to expand the notation. Okay. And the other reason I explained to you was this geometric reason where you don't want to treat points at infinity as a different thing, or you don't want to keep on talking about parallel lines not meeting in a point, or parallel lines meet at infinity, something like this. You don't want to keep on adding all the time. So you want to sort of, assimilate the points at infinity into your system. You want to be able to write them like this. So for these two reasons, we move to projective geometry. Okay, so I hope I have given you some idea of why we want to do this whole pranayama. Okay, so now coming to what this two projective plane is, and what are the points in this and stuff like that. So I will explain these things. Remember that we are going to do this in as little uh, time as possible. Okay, so we are not going too much into the depth, but I'm trying to convey to you the main ideas in this. Okay, so now first of all, the points in here, okay, this will be called the homogeneous notation. The reason for the name will be clear in a moment. Okay, this is called homogeneous notation, and this is for the same point. Okay, so xy is same as the point xy1. Let me just tell you that right now. And this is its homogeneous notation, and this will be referred to as the inhomogeneous notation. Homogeneous, inhomogeneous notation. So when I say homogeneous notation or homogeneous coordinate or homogeneous vector, we mean we are talking about the point in as seen in the projective space. And if I don't put the adjective homogeneous, then that means we are looking at the point in the Euclidean plane. Okay? So that's the difference in wording. Okay, so now why do we say homogeneous? Okay. So let's look at how lines will be represented in this new notation. So a line in the plane can always, so we are first talking about 2D. Okay, so we want to talk about projective plane. The notation for the real projective plane is R2 and sorry, what am I saying? For the real plane, real Euclidean plane is R2 and for the projective plane is P2. Okay, that's the notation. Okay, so how does a line in a plane, how can we represent it? You know that this is the standard way of representing a line in a plane. Ax plus by plus c equals 0. Okay, and if you choose different a, b, and c, different choices of a, b, c will give rise to different lines. Okay, now what I can do is instead of writing it like this, since what matters here is the choice of a, b, and c, what I will do is I will say that this line is actually represented by this vector abc. Okay. So now my line is if x plus by plus c equals to 0 is going to be represented by the vector ABC. And one thing to notice is that this correspondence is not 1, 1. Why is this correspondence not 1, 1? Because if you look at ABC and you look at any scalar times ABC, do these represent the same line? K is a non-zero scalar. So these two represent the same line in the plane, right? Both represent the same line. Why? Because well, to this, if you multiply a scalar k here, it is the line is not changing, right? Because ax plus by plus t is 0 if and only if k times ax plus by plus c is 0. So for this reason, both these are representing the same line. Okay, so this representation is not a 1-1 representation. But now what I'll do is, since they represent the same line, I'll just put them all in one set. Okay, what I'll do is I'll define an equivalence relation. Now, the equivalence class of vectors, I'm going to define an equivalence relation under the following equivalence relation. I hope everybody remembers what an equivalence relation is. What is my equivalence relation? I'm going to say A, B, C and any non-zero scalar times A, B, C are related. Okay, so for k not equal to 0. So what I'm going to do is look at the equivalence class, which means I'm putting both these in the same equivalence class. Okay, and that equivalence class is called a homogeneous vector. Okay, so equivalence class of vectors under this relation is called a homogeneous vector. Okay, so when I say the point ABC, then I will actually mean the point KA, KB, KC for all non-zero, all these points. Okay, so any so a representation, any homogeneous vector ABC will actually represent the entire class. Represents its equivalence class, the set of all k times A, B, C, where k is non-zero. Okay, what does this mean? This means that, so what is k times, so if I take any point A, B, C in R3, okay, So now because these are three coordinates, it's easier to imagine in R3. Okay. Then what is K times ABC? Look at the vector ABC in R3. ABC, suppose this is the point ABC. Okay. This is the vector ABC. What is the scalar times ABC going to give me? Where does
A
this
K B
scalar
K
lie?
B C.
Yes. Where does it lie? Where does that point lie?
On the same vector ABC, like just a scaled version of it.
Exactly. You look at the line on which this vector ABC lies. Okay. So look at this line on which the vector ABC lies. Then all these points K, A, B, C lie on this line. Correct? This equivalence class is nothing but the set of all the points lying on this line. In R3, if you look, it is the set of all these points. So when you read about projective geometry, you will also hear that a point in P2, what is a point in P2? A point in P2 is this homogeneous vector, which is actually a line in R3. This homogeneous vector represents all the points on this line in R3. Okay, so that is just a sort of mental picture for you. So now all you look at all line and passing through origin, by the way. Okay, so you look at all these lines in R3 passing through origin. Make a mental picture of all these lines passing through the origin, and every line means one point in your P2. Okay, every line corresponds to one homogeneous vector. And what is which representation you can choose? You can choose any representation. You could have chosen ABC to represent this entire line, or you could have chosen 2A, 2B, 2C to represent this. Anyone, any point you can choose. The whole line represented by a point because they are all scalar multiples of each other. The coordinates are all scalar multiples of each other. Okay. And so what we seek to do is not differentiate between points in R3 if they are scalar multiples of each other. Put them all in one equivalence class. That equivalence class is called a homogeneous vector. Okay. So this is one way of looking at it. And if you don't see, there are various ways of thinking about projective geometry. Okay. One can appeal to you and suit you for your kind of thinking, you stick with that. For somebody else, some other way of. So for some people, geometric thinking makes sense and appeals and they can think that way. Other people would like to stick to algebra. Okay. So if you want to stick to algebra, just remember this. If you want a geometric picture, take this. Okay. Whatever works for you. Okay. So this is what is the meaning of a homogeneous vector. Okay. So let me define what the projective space is. The set of all equivalence classes of vectors in R3 minus the origin. Okay, so the origin is the only point that is not represented. Okay. This forms the projective space P2. Okay, note that 0, 0, 0 does not represent this vector. 0, 0, 0 does not represent any line. Any line in R3. Okay, so we have sort of a notion now of what are the points in P2. Okay, you have a geometric picture to look at if you like, or you have this algebraic definition. Okay, so you look at all such. These are going to be called as points in P2. So now let's look at. So what I want to do now is how to represent a single point. Okay. So this is homogeneous representation. So we just represented a line. We started with a line. Okay, so we looked at homogeneous representation of lines, and from that we got all this. So now I will look at homogeneous representation of points. So now we are looking at points in. So we are coming back to this uh, here like this. Okay, look at these points. Now we want to express these points in this new notation. So a point xy. How do we express that this lies on the line L given by ax plus by plus c equal to 0? Okay, you can express that this point lies on this line, which means x and y satisfy this equation by saying that so this is the point lies on this line if and only if. Now in vector notation, you can write this way: xy1 a b c equals 0, right? So the information that this point lies on this line can be expressed by expressed using matrix notation in this way. Okay, so you can see that expressing the point xy as xy1 is actually useful for this kind of language. Okay, so what I want to say is that representing xy as xy1 is useful for this expression. So expanding notation is helping us in this also, right? Another point to note is that if you have xy1 a b c equal to 0, okay, this is equivalent to saying that kx, ky, k, abc is 0. Is this true? You agree with the statement? Then of course k is non-zero, right? So what we can do is we may consider that all these points, okay, fall in one class. This is what we would have anyway for our homogeneous representation of xy1, correct? From our earlier experience also, or earlier definition also, this is what we would have. So what I'm trying to say is that even in the homogeneous notation, saying that this point lies on this line will stay the same. The entire class in this notation will also fall in this on this same line. So we may consider the set of all k x y1, okay, as representing one point xy in R2. Okay, so the homogeneous notation will make sense for points in this way. Okay, so now we have the correspondence. Between R2 and P2 as well, your points xy in R2 will be represented by the set of points kx, ky, k for k not equal to 0 in P2. Okay, so if you want to go from R2 to P2, you will go like this. So point xy corresponds to this equivalence class. Okay, How will you go backwards? Suppose you have x1, x2, x3 here. Okay, and you want to go this way. You want to find the corresponding point in R2. Okay, then how can we get it? The following correspondence: x1 by x3, x2 by x3. Make sense? Because to this, if you were to apply this map and go back again to its equivalence class, it will be the same equivalence class, right? Yeah.
Ma'am, so is 110 not an element of P2?
Yeah, so that's a very interesting point. Let's come to 110. Okay, so in a moment. Okay, and that is the sort of points that we are doing this whole thing for. Okay, so we will come to that in a moment. So let me talk about some results. Okay. So some simple results which I am stating because we might require them later. One, that the point, so I'm going to call it sort of a bold small x. Okay, so for that bold, I will just underline. Okay. So this is the notation for a homogeneous point. Okay. So the point x, y, 1 lies on the line L equal to, so we saw that line can be given like this, ABC in P2, if and only if this X transpose L is 0. Okay, this is nothing but a restatement of what we did here. Right? This is just this xy1. This is nothing but this vector transpose times L. Okay, so just a restatement in terms of this notation. Okay. So this is shown earlier. Just one thing we need to notice in this respect is that your X transpose L could very well have been written as L transpose X in this case. Okay. And that either of these things mean the same thing as your dot product. Right. So just keep, I mean, you can go from one to the other as you like because they mean the same thing. Okay. So the point is that the simplicity of this notation is coming about because of this homogeneous representation. Okay, saying that this point lies on this line L now is like saying that X transpose L is 0. So this has simplified notation. Now you don't have to say it in so many words, or you don't have to say it in an equation or a longer equation. Okay, you can just say it this way. Okay, so just something to appreciate. Okay, then the intersection of two lines. L and L prime is, well, so let's see what it is. So suppose L is the line ABC. Okay. L prime is the line A prime, B prime, C prime. Okay. So now if you have a point X, so intersection means that point lies on both, right? That means that point, so suppose X is the point of intersection. Notice we are not even caring about whether these lines are parallel or not. We are just proceeding. If you were doing this in Euclidean geometry, you would have to say, suppose these lines are not parallel and we let X be the point of intersection, right? So now don't have to say that statement anymore. We are in projective geometry and we are not treating parallel lines or lines intersecting as infinity as a special case. Okay, it is absorbed in this entire language. So suppose X is the point of intersection of L and L prime. Okay, then what do we know? By this earlier notation, we know that X dot L is 0. Okay, and X dot L prime is 0. Right? So what can we say? How is there an expression that we can get for this X if both these things are happening?
X of L plus L dash is 0. X dot.
Plus, huh?
No, X dot L plus L dash is 0.
Um,
X dot product with L plus L dash. That should be 0.
dot product with L plus L dash.
Yes.
Do we
But that does not necessarily says ki X dot L and X dot L dash both should be 0. So yeah, that should be.
so I want to get X, right? And X is to be a vector. So do you know a vector which satisfies both these things? And so the information is only L and L prime. This is the only information. Using L and L prime, do I know a vector which satisfies both these things?
L cross
L cross
L
L.
prime.
That's right, L cross L prime. Right? We have already that L dot L cross L prime is 0 and L prime dot L cross L prime is 0. This is the vector which satisfies both equations. Okay, so we can actually take X to be L cross L prime. This cross product gives you the point of intersection. So the intersection of 2 points L and L prime is X equal to L cross L prime. This is a vector. Right? That's your vector X. Okay, so this again sort of makes things the notation simpler. Okay, so now we are getting closer to that question that someone asked a bit earlier. So this is intersection of two lines. Now let's talk about line joining 2 points. Okay, so the line, yes.
Ma'am, how did you get L cross L prime? I did not get this. Like L dot product L cross L prime equals 0.
Array, yaar, this is something you must have done in, I don't know, high school. You can check this is true for, if you take any two vectors, you can check this property holds.
Okay.
Okay. So this is dot product here, and this is the cross product, and you can use algebraic properties, or you can expand it out and check that this holds. Basically, when you do something like this, you will be looking at a matrix, and you have L and L, so 2 rows will be repeated.
Okay. Okay.
Yeah, so something like that.
Yeah. Okay.
So this is sort of well known. Both these things. If you have a repetition here, then you get this product to be 0.
Okay.
So the line joining 2 points X and X prime is given by, now let's try to guess this. Okay, so you have X and X prime both lying on L. Okay, so by the same token now we'll see. Okay, X lies on L, so X dot L is 0. Okay, so let L be the required line. And X dot L is 0 and X prime dot L is 0. And so what should L be? You're given x and x prime, and you want to find L, which satisfies both these equations. It is x cross product x prime, right? By the same token as before. So the line joining 2 points, x and x prime, is given by x cross product x prime. Okay. Yeah. So I hope you can appreciate how simple the notation has become, the language of intersection of lines or line joining 2 points and so on in terms of the given information. And now finally we talk about intersection of parallel lines. Okay, so this was sort of the aim, okay, so that you don't want to make a special case of this intersection of parallel lines. And we want to say that, you know, this thing follows the same kind of rules. You will be able to say the same kind of statement even if you have parallel lines. Okay, so by what we wrote above, okay, so by 3, so the parallel lines, let me call them L and L prime. Okay, intersection of parallel lines L and L prime. By 3, their intersection should be sorry, intersection I talked about earlier. By 2, I should say, not by 3. By 2, their intersection should be L cross L prime, right? This point. So should be X equal to L cross L prime. But what is L cross L prime? That is X equal to L cross L prime, which equals, so L could be some ABC. L prime is some A prime, B prime, C prime, but these are parallel lines. Okay, so parallel, see, remember where this notation came from. ABC stands for the line AX plus BY plus C equal to 0. This line in the plane. Okay, a parallel line will have what kind of equation?
A,
Scalar
B,
multiple
C
of
plus D.
Sorry,
this
what?
scalar. So C would be something else. That's all.
Your C will change, right? This y-intercept could be something else, but A and B will be the same, right? So that means L prime is going to look like A, B, and some C prime because these lines are parallel. Okay. So now you can take the cross product of these two vectors and check that this comes out to B minus A 0. Okay, you take cross product like you did in school. You take I, J, K, A, B, C, A, B, C prime. Okay, this is what you will get. Okay, now what does this point mean in inhomogeneous notation? So this is homogeneous notation, right? Remember, this is your homogeneous notation. What does this point mean in inhomogeneous notation, which means in R2? How do we go back? I had given you a sort of way of going back, right? This way. You divide by the third coordinate. That is how you go from points in P2 to points in R2. Now, if you divide by the third coordinate here, so in inhomogeneous notation, this point stands for what? This point stands for B divided by 0 minus A divided by 0, which is a point at infinity. Right? Yeah. So did this match our expectation? That the intersection of parallel lines should be a point at infinity? Yes, right? And this point at infinity has been expressed in the same homogeneous notation, just like any other point in P2. Okay. So points of the form x, y, 0 are exactly the points at infinity in this notation, in the homogeneous notation, because they will correspond to points of the inhomogeneous notation. This will be the point x by 0, y by 0, which is a point at infinity. Okay, so having this third component 0 corresponds to having points at infinity. Okay, any questions? You can take maybe 10 seconds, let this sink into your mind, and then you can ask a question if you have any. Okay, so this observation, okay, agrees with our usual idea that parallel lines should meet at infinity. So this statement is worth writing down. So this observation agrees with the usual idea that parallel lines parallel meet at infinity. Okay, and this is how the projective notation takes care of this special case. Now you no longer have to keep on making a special case out of parallel lines meeting at infinity. They are just going to follow the usual rules that we wrote in 2 and 3. And they are just like the infinity is just like any other point in the plane. Okay, and we need this expanded notation because in the image taking process, you don't want to keep talking about horizon. Okay, you remember in that pinhole perspective, I explained this concept of horizon, right? You don't want to make a special case out of it every time. You just want to treat it as any other point in the image. Okay, so that you can think that that is sort of a uh, how do you say heuristic sort of reason why you want to look at the projective plane or use this notation. And the other very practical reason is that you want this expansion of notation, what I explained earlier here. Okay, you want to be able to write in the end that the world point is acted upon by some matrix and you get the image point. And this is not going to happen with your usual linear algebra in R2 because translation is not a linear transformation. Okay, and so also you need an expansion of notation. Okay, so expanding your notation from R2 to P2 takes care of both these things. Okay, so I hope I provided you some motivation and some basic understanding of what we are doing here. Okay, so definitely you will have to go through this once more, till once or twice more till you get a bit comfortable. Okay, so in general, points in P2 that have the last coordinate 0 will be called ideal points, or these will actually correspond to points at infinity. Okay, sometimes they are called ideal points, but I mean we will not follow this or use this language so much. Ideal points. These are the points at infinity. The points at infinity on the R2 plane. Okay, so P2 is nothing but R2 together with these ideal points. That is what P2 is. Okay, notice that this is a sort of As I was saying, you are not changing the space, you are just changing the notation for it. Okay. And now in this new notation, what you have this P2. This P2 is not actually a vector space. Okay, your R2 is a vector space. P2 is not a vector space. Notice that. Guess why? P2 is not a vector space. Does it have an additive identity? So does it have the 0.000 in it? There's no addition or additive identity. Okay, so this is this space that we have got, although it is sort of expanding notation for us, taking care of this axiom of parallelism and so on. It is not a vector space, so you cannot deal with it as you would with R2. Okay. However, you can still describe geometric objects in this space. Like we have described a line, we have described a point, you have described line joining two points, intersection of two lines. All these things you can still do because for this you don't need the vector space structure on it. Okay. So, but you have to keep in mind that this is not a vector space. We will still be talking about the projective transformation, which means a map from one projective space to the other. Okay, but that has nothing to do with a linear transformation because a projective transformation is not linear. The only thing that is good for us is that this projective transformation we will express as a matrix. Okay, so that matrix is what is going to take the world point to the image point for us. Okay. Then there is a small section on conics in P2. Maybe for now I will sort of skip it. Okay, maybe you are too saturated with this. You can think about this a bit. And this conics part I will maybe talk about next time. Because what I want to do right now is just define a projective transformation, okay, and then end the class. Okay, so I will just define projective transformations. So conics. Otherwise, let it be. I will just finish this part on conics. Okay? There's no point in. Yeah, we are anyway out of time, right? I have to finish in 5 minutes. Okay, so let me talk about conics and P2. Conics. Well, the equation of a conic in R2, you remember? Equation of a conic in R2 is given by what? If you remember, it is a quadratic, general quadratic equation, right? Ax square plus bxy plus cy square plus dx plus ey plus f equal to 0, right? This is a general polynomial of degree 2. And this is how you state a general conic in R2. Okay. Now what we are going to do is try and replace. So xy is the inhomogeneous coordinate, and I'm going to replace it by the homogeneous coordinate. Okay. So what I'm going to do is replace xy, okay, by instead of xy, let's put x1 by x3, x2 by x3, 1. Okay. So it's like you're still in the same space, you're still in R2 because this is 1. Okay. But instead of writing xy, I'm going to write x1, x2, x3. Okay. So that it will make the make the conversion to projective coordinates easier. Okay. So if I do this replacement, then I mean you can put it in, simplify, and check that the following is true. Okay. So replace this, and what we get is a x1 square plus b x1 x2 plus c x2 square. This is easy to see how we will get, plus d x1 x3 plus e x2 x3 plus f x3 square. When you take that least common multiple, okay, this is going to be 0. Okay, this is how the equation of conic will look like in these coordinates. Okay, and now I can write this in matrix form as follows. We can express this in matrix form as x transpose c x, okay, where C is the matrix. So X underline, you can guess what X underline is going to be. It's going to be X1, X2, X3, right? And C is A, B by 2, B by 2. This is symmetric. We see F, B by 2, B by 2, B by 2, B by 2. Okay, this is symmetric. This is the coefficient matrix for a conic. Okay. This C is called coefficient matrix for a conic. Okay, so you can be given any symmetric matrix like this, and that will give rise to a conic equation like that. Okay, multiplying. So the point now is that multiplying C by a non-zero scalar will not. If you multiply C by a non-zero scalar K, that's like multiplying this equation with K. Okay, that's not going to change. So C is in fact a homogeneous matrix. Right? It does not change the conic. Multiplying C by a non-zero scalar does not affect the equations, does not, or equation does not affect the equation of the conic. So what we have actually is C is a homogeneous representation of the conic. You could write C or you could write any scalar multiple of C, does not matter. It is a homogeneous representation of the or of a conic. Okay. And when we have a homogeneous representation like this, later on we will have to worry about how many degrees of freedom are there. Because these degrees of freedom will determine how many equations we require to solve it. How many degrees of freedom are here? The number of degrees of freedom is always, okay, if you have an equation, I shouldn't say always, if you have an equation like this, okay, then it is the number of scalars minus 1. Because if you knew A, B, C, D, E, you could calculate F. Or if you knew any 5 of these, you could calculate the last one. Okay, so the number of degrees of freedom here is 5. Okay, so the conic has 5 degrees of freedom, which means if 5 are known, the 6th can be found. If 5 quantities out of the 6, which 6 quantities? A, B, C, D, E, F. If 5 of these are known, the sixth can be found. So we have that equation. Okay, so in this way, the conic has 5 degrees of freedom. All right, so let me stop here. Okay, and on Thursday, I will talk about projective transformations, and then we will talk about the other 2 points on the agenda, which was to model of the pinhole perspective as a central projection and talk about how you can remove perspective distortion using a discrete linear transform. Okay, any questions so far?
Ma'am,
Yes.
I wanted to ask about this assignment one second question that you have given. Uh,
Yeah, can you? Oh, yeah, that,
the monument image.
correct, yeah.
Yeah, so that image already has 3 channels, and then you told to split it out into 3 parts and then merge it together.
Yeah, so the 3 channels, I asked you to separate them. I mean, cut that image because it has been stacked one above the other, right? So you cut that image into 3 parts, the 3 channels. Then, I mean, so is the question not clear to some people? So what I want you to do is, so you have this image, and I have told you which one is red, which one is blue, which one is green, right? So,
Yes.
what is the first one?
Blue, green, red.
Blue, green, red. Okay. So you have this. So you cut it first. Okay. You cut it at the. You find the size of this. You divide it into 3 parts. You correctly cut it. Okay.
Yes.
So then you will get your separate blue channel, green channel, red channel. 3 channels you've got. Okay. Now what you have to do is you have to align them pixel by pixel, which means you have to find here which pixel sits over the
Ma'am,
first one.
ma'am, that is clear. But
Hmm.
what I'm trying to say is that this tagged image that you have given us, it's a single JPG file.
Hmm.
That image itself has 3 channels.
Yeah.
As in 3 channels means its dimension is WH comma 3.
Yeah. So just read it as a grayscale image.
Oh, I see.
No,
Oh,
no,
yeah, yeah.
it's
Okay,
the
yeah.
all
You
3
will
channels
have
are
to.
the same. Just read them as
Yeah,
a.
you can just take one
Yeah,
of
the
them.
values for all 3 channels are the
They're
same.
same.
Oh, okay.
So,
Fine.
or you can, do this grayscale transformation. Just
Okay.
say grayscale and yeah, that's right.
Okay. Fine.
What I did was just for 3 coordinates, just make 2 coordinates 0 for all one image and so on.
Yeah, which means you just choose, what is, you just choose the first or the second or and take
Yeah,
these
the
three
first component of everything. Anyways,
channel. Yeah, just take the first component and ignore these and save that as a separate image.
yeah.
Or you
Okay.
can just use cv.grayscale, I think, or gray something. Color
Okay.
to, I don't remember exactly, or it is called, it's a function in CV2 which takes BGR or RGB to
No,
gray.
while using IM read only, you can give grayscale
Yes,
as a.
exactly. That's right. In
Flag is
MV,
equal to 1. Yes.
Yeah,
yes,
flag is
yes,
equal to
0.
zero, I
Flag is
think.
equal
But
to
yeah,
0.
flag is
Yeah.
equal to 0. Yeah.
Yes.
correct. So then that way you can just choose the one channel and then use that to do the rest of it.
Okay.
So
Fine.
what I want to say is that, in this aligning is a little bit something I am asking you to do because it is not true that after you've cut the first pixel here will align with the first pixel here. I mean, if you do that alignment, you will not get the best sort of image.
Also, the alignment that within the range of -10 to 10 pixels, like shifting it, it needs to be done only vertically, right? Because horizontally, I think they are already aligned.
What have I asked you to do? I don't remember the wording, but probably you should do it in these directions, no? At least. What have I asked in that question?
1 minute. I'll tell.
Did I say what? Let me also open that one. I don't remember if I specifically said which direction.
The word is search over a window of possible displacement, say -10 to 10 pixels. That is the wording that you have given.
Yeah.
So
Yeah, so
After,
usually, I would say 8 directions like this.
okay,
Then you can take the minimum of the SSD along these 8 directions. You can also take 4 if you don't want to take 8. Okay. But I think you will get a better. You can increase this if you like or decrease it.
okay, fine.
They are horizontally aligned. I didn't know that.
Yeah, they're horizontally aligned. I am telling because I was visualizing the stacked image together.
Ah.
And yeah, the left part and right part boundaries are exactly same for both of them. Like visually, they're the same. Maybe 1 or 2 pixel difference might be there.
Don't do, yeah, don't go by what you see visually. I mean, go by
Okay,
number.
okay, fine. I'll do it.
Yeah.
Also,
So I
ma'am,
would suggest do these 8 directions. I mean, this is the minimum you can do. Don't do 4. It will not be, I mean, very good result.
Okay, fine.
Yeah. Yeah. So next, somebody's asking.
yeah, so I just wanted to ask you, once the images are aligned and we have to give the colored image back. So, should we have like, do we have to give a cropped image or the whole thing merged
The
together? Like,
whole thing. The whole thing. I think even when you do all this very carefully, the boundaries, there will be bands of colors.
yeah, that's for sure.
Yeah,
Yes,
it's
even while aligning, very small part of it would be cropped. Because if I want either we have to pad it up for matching the dimensions, or we have
yeah. It is possible that the aligning is not what the earlier. I don't know who's talking, but what the earlier person was saying, right? Horizontally aligned. It is possible they are not. So you have to pad. You can pad with zeros. Okay, so look up how to pad an image, which means you have an image of a certain size and you require to increase the size. Okay, that's called as padding. And there are various ways of doing padding. Okay, you can pad with zeros so that doesn't affect much.
fine.
So yeah, you might have to pad to align them together. If you don't pad, I think you will have a band of red or a band of blue or green, something appearing. And so if you don't do padding, I will still accept the solution. It's not that. What I really want to make you do is do that SSD calculation over those in those directions, choose the minimum and do the aligning properly. That's what I want. Yeah.
One more question, ma'am. When you said do the sliding in 8 directions, I didn't understand how would you do it in the diagonal directions. Like right now, I'm doing it in vertical and horizontal direction.
Yeah, so in the diagonal direction, you will have to say how many spots it has to go like this. So you will have to.
But wouldn't this be covered in the right and left horizontal and vertical direction?
No,
If
here
I'm
you are.
doing if I'm doing 2 loops over -10 to 10 in both directions, then will this not be covered in that?
Oh, like that you're doing. You're
Yeah.
doing. Yeah, then so you're doing for and for, right?
Yeah,
So in
for
the outer
-10 to
loop,
10
you
in
are letting.
horizontal and yeah.
Yeah, so for sure, you're letting x vary from -10 to
To 10 and
10
y
over
vary from
2.
-10 to 10. Yeah.
Oh, then
Yeah.
that's not only 8, that's many directions covered.
Yeah, then you are
Yeah.
covering lots of them. Yeah, very good.
All of them.
No
Yeah.
problem. Yeah. So if you're doing a nested for loop, you will cover everything. Yeah.
Okay.
Fine. Yeah, anything else? Okay, so then if there is